Welcome class 10. Today we will do some numericals from the chapter machines. So the first question we have from page number 59 is question number 3, which reads, a force of 5 kgf is required to cut a metal sheet. A pair of shears used for cutting the metal sheet has its blades 5 centimeters long while its handles are 10 centimeters long. What effort is needed to cut the sheet? So let's look at the solution. First, we'll write down the information obtained from the question. So every time, whatever is given in the question, we'll write it down out here. So over here, the force of 5 kgf is required. So that will be the force required as load, that is equal to 5 kgf. Now the length of the blades, that is the load arm, okay, is given as 5 centimeters long. So it is 5 centimeter. And length of handles is equal to 10 centimeter. That is over here it's given. All right. So length of handles, that is the effort arm, equals 10 centimeter. Now since we know that load into load arm becomes equal to effort into effort arm, so the load is 5 kgf into load arm is 5 centimeter. Effort is what we have to find out. So effort into effort arm is 10 centimeters. So here we didn't convert centimeter into meter so that it comes into SI system. You can convert it into SI system also, but since here in both the cases load arm and effort arm both will be centimeter and centimeter, which can be cancelled out, so here I didn't convert the unit into meter. So you can use 5 centimeter and 10 centimeter respectively out here because those units are going to cancel. So it will be 5 into 5, 25, and when 10 divides 25 we'll get 2.5. And since the load is given as kgf, therefore your effort will also be 2.5 kgf, and that is the required answer. Next is question number 5. A man uses a crowbar of length 1.5 meters to raise a load of 75 kgf by putting a sharp edge below the bar at a distance of 1 meter from his hand. Draw a diagram of the arrangement showing the fulcrum, load and effort with their directions. Number B, state the kind of lever. Number C, calculate load arm, effort arm, mechanical advantage and the effort needed. So here this is the question. Now let's look at the solution. First we have to draw the figure. So the figure is like this. It's a crowbar and it's lifting the load, and here as the question says there is a sharp edge below the bar at a distance of 1 meter. So that means from this point to this point it is 1 meter. That is, the hands will be kept out here. So up till from this point to this point it is 1 meter and there is a sharp edge. So here it will be the fulcrum, effort is out here and the load is down here. So since load is acting downwards, effort will also be acting downwards so that load can be lifted upwards. Okay, so this is the required picture. Now we have to find number B. We have to state the kind of lever. So since the fulcrum lies in between, therefore the load and the effort, it is a lever of class 1. So this is the first class lever, as we have already learned that crowbar is a first class lever. So here from the figure itself, since fulcrum is in between, so we can say it's a class 1 lever. Next we have to find out from the question number C, we have to calculate the load arm, effort arm and the mechanical advantage and also the effort needed. Now here the crowbar has the total length of 1.5 meter to raise a load of 75 kgf. So let's look over here. The load arm, since the total length of the crowbar is 1.5 meter and it is 1 meters away, there is a fulcrum. So from here to here it's 1 meter and the total length is 1.5. That means the load arm is between the fulcrum and the load, that is equal to 1.5 minus 1, that will give us 0.5 meter. All right, and the effort arm is equal to 1 meter, that is the point from where the effort is used up to the fulcrum, that is the effort arm, and that is equal to 1 meter. Now we have to find the mechanical advantage. This is answer for number 1, load arm. Number 2 is effort arm. Okay, 1 meter, second answer. Thirdly, we have to find the mechanical advantage, which is equal to effort arm divided by load arm. When you divide effort arm, put the value 1 meter. Load arm is 0.5 meter. Okay, so 1 divided by 0.5 is equal to 2. Here the units are cancelled, so we don't need to write the units. So mechanical advantage is equal to 2. Number 4, we have to find the effort. So we use load into load arm equals effort into effort arm. So the load is equal to 75 kgf as it is given in the question, which is multiplied with the load arm 0.5 meter equals effort that we are supposed to find out into effort arm, that is equal to 1 meter. So when you calculate this, 75 into 0.5, that will be equal to 37.5 divided by 1, again is 37.5 kgf. That is the required value for effort. Next we have question number 8. Let's read the question. A lever of length 9 cm has its load arm 5 cm long and the effort arm is 9 cm long. To which class does it belong? Draw a diagram of the lever showing the position of the fulcrum F and the directions of both the load L and effort E. What is the mechanical advantage and velocity ratio if the efficiency is 100%? Number D, what will be the mechanical advantage and velocity ratio if the efficiency becomes 50%? So first of all, we focus on the question, whatever is given. So we write down the data. So a lever of length 9 cm, that means the total length is 9 cm, has its load arm is 5 cm. So let's write it down. Length of the lever is 9 cm. Length of load arm is equal to 5 cm. And the effort arm is 9 centimeters only. So length of effort arm is 9 cm. So if you look closely, then the total length of lever is 9 cm. And the length of effort arm itself is again 9 cm. This means that load arm, that is the load lies in between the fulcrum and the effort. So if the load lies in between, then this must be the lever of class 2. So the picture might be something like this. So here is the entire length of the lever, which is 9 cm. And since the load is kept in between, therefore the load arm will be equal to 5 cm. That is load arm is the distance between the load and the fulcrum. So here is the fulcrum at one end. Therefore the effort arm will be the distance from effort to the fulcrum. That is effort arm is exactly 9 cm. So this is what we see in the picture as well. Now we have to draw the figure. So this is the figure drawn. Now number C, what is the mechanical advantage and velocity ratio if the efficiency is 100%? So now we know that efficiency is given as eta, which is equal to 100%. Now 100% means equals to 100%. 100 out of 100 is equal to 1. And the mechanical advantage we can find out using effort arm by load arm, which is the formula. Mechanical advantage equals effort arm by load arm, that is equal to effort arm is 9 cm and load arm is 5 cm. So 9 by 5, which is equal to 1.8. Now also we know the formula that mechanical advantage equals velocity ratio into efficiency eta. So we can say mechanical advantage equals VR velocity ratio into 1, that is efficiency, This means mechanical advantage and velocity ratio will be equal. If the efficiency is equal to 1, then these two values will be equal. So if these two values are equal, then velocity ratio will also be equal to 1.8. That is the value of mechanical advantage. So this is question number C. Next, in question number D, what will be the mechanical advantage and the velocity ratio if the efficiency becomes 50%? Now the efficiency has reduced to 50%. So efficiency is now 50%. Then the mechanical advantage is also reduced by 50%. So mechanical advantage becomes equal to 50% of its initial value, that is 1.8. So 50% of 1.8 equals 0.9. Now the mechanical advantage is equal to velocity ratio into efficiency, that is 1 by 2, because 50% means 50 by 100, that is equal to 1 by 2. So mechanical advantage equals VR into half. So VR is equal to cross multiply MA, mechanical advantage, into 2. So that is 2 into 0.9, which is equal to 1.8. So 1.8 is the velocity ratio and mechanical advantage is 0.9 if efficiency is reduced to 50%.